So this is our second lecture. Yesterday, I tried to make a general introduction on the main observational facts that are necessary to understand the physics of GRBs. And I have also started to introduce the main ingredients of the physical model. And so I will go on today with the last ingredient, the fact that we need a relativistic ejecta. I introduced that yesterday, but I didn't have time to make the full calculation. And then I will start to go into more details about some aspects. I will discuss progenitors, central engine, relativistic ejection, and then the physics of the prompt and the afterglow emission. Okay, so if you remember, we gave several arguments to say that gamma ray burst, either short or long, must be associated with an initial event, which is a gravitational collapse, leading to the formation of a very compact source, either a neutron star or more probably a black hole. And then the next point is to understand that the gamma ray prompt emission cannot be produced directly by the central source, but has to be radiated from a relativistic ejecta ejected by this source, and the radiation is produced at large distance from the source. So the idea is that this is a old argument, which is found in many cases in high energy astrophysics. This is the so-called compactness problem argument. This is the fact that if you put all the energy radiated in gamma rays within a very small volume, the density of gamma rays is so high that most gamma rays should disappear due to the pair production reaction. And you should not observe the non-thermal spectrum extending above 1 MeV. So I gave this argument yesterday, and today I would like to explain more precisely how we can derive a minimal value for the Lorentz factor to solve the problem. So you remember that the pair production reaction gamma-gamma giving a positron plus an electron has a threshold, which is given by this relation. So the product of the two energies in unit of MEC square should be larger than 2/1 minus cos theta, where theta is the interaction angle between the two photons. And then there is a complex cross-section, but as I said yesterday, it can be well approximated by a Dirac function at an energy which is twice the threshold of the interaction. And as it's an interaction between photons giving leptons, it's not surprising that the normalization here is the Thomson cross-section. So to do the precise calculation, we need an additional argument, which is the spectrum of seed photons at low energy that a high energy photon will fill. The idea is that a high energy photon will cross many low energy photons, will interact with them, and we want to find the condition for allowing the high energy photon to still escape from the source. So for that, we need the observed soft gamma ray spectrum, and I've skipped some details, but what we can show that for checking the escape probability of a high or very high energy photons in gamma ray burst, we have to consider for the seed photons the high energy part of the soft gamma ray spectrum. So that's why I use a power law with an index minus beta, which is typically 2.3 as observed in gamma ray burst. And here, this is just a normalization factor, so that the integral of this quantity above the peak energy of the soft gamma ray spectrum gives this total energy, E gamma iso, high energy, because it's only the high energy part of the soft gamma ray spectrum. So if you want to have typical values in mind, the peak energy is typically above 100 keV, between 100 and 200 keV, and beta is of the order of 2.3. And we want to use this seed photon spectrum combined with this physics of the gamma-gamma interaction to deduce the probability for high energy photon to escape. And even before Fermi, we knew that there were escaping photons above 1 MeV. So typically, the maximum observed energy is well above 1 MeV. Okay. So here, I will just switch to my blackboard to do the calculation. So sorry, 1 second. So it should work. So what I will compute is what we call usually in astrophysics an optical depth. So here, the optical depth for the gamma-gamma interaction. And for those who are more familiar with the concept of mean free path, you can see this optical depth as the ratio of the true size of the source over the mean free path for the gamma-gamma interaction. Okay. In other words, the escaping fraction is of the order of exponential of -2. Okay. So I will compute this gamma-gamma opacity for the high energy photon. The gamma-gamma, the optical depth is Lorentz invariant. You can compute it in your preferred frame. And here, I won't specify the frame at that point, because then I will apply my formula to several situations. But I will just assume that I am in a frame where the photon field is quasi-isotropic, so that I can compute easily the probability to have the interaction with a given angle theta. So in this case, the optical depth will be an integral over the path of the photon within the source, times an integral over all possible interaction angle from 0 to pi. And so this is my solid angle associated to this interaction angle. Then I have to make an integral over the spectrum of the seed photons. So I have to be above the threshold of the reaction, and I can integrate up to infinity. So this is what I will call the low energy seed photon. And then my distribution of photons is given by this quantity. So it's a photon density per unit energy per unit solid angle. It's computed at this energy. So if you want, these are photons per cubic centimeter per keV per steradian. I have, of course, to multiply by the gamma-gamma cross-section. I have to compute it at this energy, knowing that I interact with the photon at this energy with this angle. And of course, I have, as always, in a reaction rate. Sorry, I'm escaping from the blackboard. So, oops, my blackboard is too small. So I will. This is continuated here. Okay, this is a continuation of that. Oops. So I have my cross section. And then, as always in a reaction rate, I have to take into account the relative velocity. It's a little more complicated for photons, but at the end, I just have a correction, which is 1 minus cos theta, where theta is the angle between the direction of the two photons. Okay. So I have to compute this complex integral. And then the idea is that I will show in a first step that if I compute it for a small compact static source, tau is well above 1, meaning that no high energy photons can escape. And then I will compute how large must be the Lorentz factor of a relativistic ejecta to have tau well below 1. Okay. So to compute this integral, I can first use the fact that I know the threshold for my interaction. It is given by this quantity. And I can have an approximate formula for my cross-section given by a Dirac function at the energy of at twice the energy of the threshold. Okay, so if I do that, then I can compute my integral. So I don't know if you see it here. So I will consider that my source is homogeneous. So the integral over the path is just the size of the region. Then the integral over the omega is just 2 pi sine theta d theta, the usual solid angle. Then the last integral is easily computed because of the Dirac function. So I can just say that this is dn over dE. I will, as I said, I assume that I am in a frame where the photon field is isotropic. So the 1 over d omega is just 1 over 4 pi. It's the same density in all directions. And I have to compute that at the threshold of the reaction. Because of the Dirac function, you see that here the variable is a ratio of energy. So for dimension conditions, then I have to multiply by 2 times the energy of the threshold, just mathematics. And then I should not forget my cross section, so which is sigma Thomson, and 1 minus cos theta. Okay, so I have a new formula, which is a little simpler. I have already suppressed 2 integrals over 3. And so now I just have to replace the threshold energy by the correct quantity, but I should know what is the density of seed photons. So the density of seed photons can be deduced from the observed spectrum. So this observed spectrum are photons per keV. I assume that I know the distance from the source, so I have corrected the flux from the distance to get photons per keV. Then I have to multiply by this term, which is just a necessary term if my frame of calculation is different from the frame where I measure the observed energy. And this factor is equal to just the ratio of the 2 energy, because if you have a Lorentz transformation, the Lorentz boost is the same for all energy, just a linear relation. Finally, to go from a photon number to a photon density, I have to divide by the volume of my region. And if I replace with the formula I gave on my slide for the observed spectrum, the result is simply something like that. And here, notice that due to the linearity when you change, when you transform energy, when you change the frame, the ratio of the observed energy over the observed peak energy is equal to the ratio of the energy measured in my new frame divided by the peak energy in the same frame. Okay. So now it's just a question of introducing this quantity here, and I will have the final result. So maybe I will do that like that. So I should try to not forget any term. Okay. Then these terms. So now it becomes a little more complicated. I have to replace E by twice the threshold, which is 4 MEC squared divided by my high energy photon, and here I divide by peak minus beta, and I should not forget that I have a 1 minus cos theta, which was here to the power beta. Okay. So I have done that. I should add this term here. I have, of course, my cross-section here. And finally, my integral. And this is just a number.
I'm sorry to interrupt, but we are not able to see. Yeah, now we are able to see the right edge. Thank you.
Sorry?
Oh, no, initially we were not able, the right edge of the page was getting cut off. Now we are able
to.
Yeah, yes.
So I have more or less finished the calculation. The last part is just a little technical, but once I have, I know exactly where I have to evaluate my integral at which energy, which is twice the threshold. Then it's just technical. I have to know the shape of my spectrum, and I get this formula. And I skip the last part. This is just a number depending on beta. It's not a problem. And so I can show what is the final result. The final result is this expression. Okay, oh, sorry. Oops. This expression. So this is the number. It's not important. Here, it's a normalization, which is more or less the number of seed photons. You see, this is the total energy divided by the peak energy of photons. Here, it is a geometrical factor, which is the ratio of the size of the region divided by its volume. And here, this is more or less the ratio of the threshold energy divided by the peak energy for a Felson interaction at a certain power, which is due to the shape of the spectrum. So now the idea is that I would like first to evaluate this quantity, this optical depth, for a static source. So for a static source, from the causality argument, I can assume that the size is of the order of c, the speed of light, times the variability timescale observed in the gamma ray burst. So I take that for the size of the region. I will assume a spherical region, static region, so this is the volume. And I can assume that the radiation field is isotropic within this source. So my frame is just the same frame as the frame of the observer. So the peak energy is equal to the observed peak energy, and also for the energy of the high energy photon I am considering. I introduce that in this big formula. I put typical numbers for the maximum energy. Remember that in practice it's above 1 MeV, for the peak energy, for the radiative gamma ray energy, for the variability timescale. and I get a huge number, higher than 10 to 15. It means that the mean free path is 10 to minus 15 times the size of the source. So the probability that high energy photons above 1 MeV can escape the source is virtually zero. We should not observe the observed non-thermal spectrum. We should see a thermal spectrum due to the produced leptons with a cutoff above MEC squared. So now I can try to solve this problem using a relativistic outflow. So if I use a relativistic outflow, the conditions are changed. The idea is that first, the radius where the emission is produced can be much larger because of the relativistic beaming. I don't see the full emitting region. I see only a small fraction of this emitting region, which is pointing towards me and beaming, due to the relativistic beaming photons in my direction. And as the beaming angle is of the order of 1 over gamma, it means that I see only a fraction which is very small, which is 1 over gamma squared. And then it means that from the causality argument, I can apply this causality argument only to this small region, and the true size of the region is gamma squared larger than before. Then there is no reason to assume that in my fixed frame, the seed photon radiation field is isotropic because of the relativistic beaming. Again, I should have much more photon in the direction of the motion. But if I come back to the comoving frame of the emitting region, then I can still assume that my radiation field is isotropic. So I will carry the calculation in the comoving frame of the emitting material. And then due to the Lorentz transformation, the size I have to consider is this side divided by gamma, length contraction. Then for the volume, as the relativistic motion is only along the radial direction, the surface is unchanged, and this is just the width that has to be modified due to the length contraction. So I can take that for the volume. And then due to the Lorentz transformation, in the comoving frame, all energies are reduced by a factor which is of the order of the Lorentz factor. So I divide all my energies by gamma. Then I implement that in the same formula, and I guess I get a final result which is very close to the previous one, except for a prefactor which depends on gamma. And if I take a typical value for the Lorentz factor, which is of the order of 100, then I get an optical depth which is much closer to unity. Meaning that if the Lorentz factor is of the order of 100 or more, then photons, high energy photons, have a real chance to escape the source. So this is the solution. I need an ultra-relativistic outflow. And then if this is, if the emission is produced from an ultra-relativistic outflow, you see that the emission is produced very far from the central source by the, it's typically at a distance which is gamma squared times the initial size. Okay. So as this estimate of the radius is important, I will just make a short additional calculation just to prove this formula. Here I have finished the main argument for the gamma-gamma annihilation. I have shown that if the Lorentz factor is high, the source becomes transparent for the gamma-gamma reaction and high energy photons can escape. But this calculation is entirely based on this estimate of the size of the emission region. So it's important to demonstrate this result. So what I will do is when I will provide the slides, I will include in the PDF of my keynote, I will also include a scan of the calculation I'm doing on the blackboard for those who would like to test the calculation by themselves. So the idea is very simple. If you assume an ejecta, which is, for instance, at that stage, I can assume a spherical ejecta, and an observer which is in this direction, okay? And if this ejecta has a relativistic motion with a Lorentz factor gamma, then it means that, for instance, this emitting region here is beaming photons within a solid angle which has an opening angle 1 over gamma. So it means that I can still observe photons coming from this region. It's still beamed in my direction, but if I consider photons emitted here, for instance, well, no hope for the observer to detect these photons. So it means that the region that can be really observed, detected by the observer is only this region here, which is limited by an angle 1 over gamma here. And then I can deduce what is the minimum variability timescale I can have from such a relativistic source. If you assume that the whole sphere is flashing instantaneously, which is unphysical, you need some time, but you assume that the sphere is flashing instantaneously. So the duration of the emission is 0 in the lab frame, okay? Then, due to the speed of light, as the distance to reach the observer is a little smaller for this, for photons emitted here compared to photons emitted here, I will add a difference of arrival time for these photons, which will be the distance, the horizontal distance between these 2 points, which is r times 1 minus cos of the angle 1 over gamma, divided by the speed of light. And if gamma is large, if I am ultra-relativistic, but it is always a good approximation for gamma ray burst, because just before we demonstrated that we need Lorentz factor above 100, then I can make a Taylor expansion of the cosine, and I get this expression. And this should be smaller than the observed variability timescale. Otherwise, it means that my emission is smoothed over a longer timescale, and I cannot observe the sharp timescale variability. And this leads to my condition, the condition I used in the slide before. So this is a very important point in gamma ray burst physics. This is how it is able to, it is possible to maintain a short timescale variability, even if the emission is produced far from the compact star. We still, from the compact source, we still need a compact source, because we will see later that the variability of the light curve is still associated to the variability of the central engine. So we still need a compact source to have the central engine varying over a millisecond timescale. But due to the relativistic beaming, the emission can be produced at much larger distance. Okay, so I come back to my slides. I don't know if there are questions for this. Yes, I see questions. So 1 second. So there is a good question about the possibility for an observer to distinguish between a sphere and a jet. It's a good question, and during the prompt phase, if, and this is what is usually assumed, if the ejecta is a jet, but a jet with a physical opening angle that I could call theta jet, which is much larger than 1 over gamma, then there is no hope for the observer to distinguish this jet from a sphere, because in fact, the observer is receiving photons only from a very small fraction of the emitting surface, and it's not possible to know if this is a small fraction of a cone or of a sphere. But I will show later, when I will discuss afterglow physics, that during the afterglow phase, the jet is decelerating, so the Lorentz factor is decreasing, so 1 over gamma is increasing, and then if we are indeed observing a jet, 1 over gamma can become larger than theta jet, and for the first time, the observer can distinguish a jet from a sphere. So this question is a very good one, but it's more relevant for the afterglow phase. Okay, so I will come back to my slide. Okay, so now we know that we have a relativistic ejecta, and then, of course, a very complex question is to know how it is possible to produce such a relativistic ejecta with a very high Lorentz factor. The final Lorentz factor should be of the order of 100 or more. It's a complex question. I will discuss it a little later for more realistic models, but I would like here to mention the fireball model, which is unrealistic, but is simple and is somehow, I would say, the reference model with which you can compare more realistic models. So the fireball model is a purely hydrodynamical model. You assume that you put all the energy in a thermal form in a very small volume, and then you let it expand radially to become relativistic. So the equations of the fireball are quite simple, and so we can derive them together, and we will get a first characteristic radius, which is important for gamma reverse physics, which is the acceleration radius. At which radius do we reach the final Lorentz factor, which is above 100? So to do that, I need to come back to my blackboard. I'm sorry, it's a little complicated to switch every 2 minutes, but it's a problem of doing such a course remotely. Yes, okay. So, in principle, to solve the problem of the fireball I have just described, I would need to write the full set of equations of fluid dynamics in special relativity for a spherically symmetric outflow. It is a little complicated, so I will assume, and this is something we can test the validity of this approximation later, I will assume that each part of the fireball is evolving independently of the other parts, meaning that I can neglect all pressure waves propagating within the outflow, all interaction between various shells at various radii. And this is valid as long as the relative velocity between different parts of the outflow are small enough to avoid such an interaction. So if I can do that, assuming that plus ultra-relativistic motion, then I can reduce my equation of fluid dynamics to a set of 3 steady-state equations: conservation of mass, so for those who are not familiar with special relativity, you recognize, sorry, there's a missing C. You recognize some, if the Lorentz factor would not be here, you would recognize a standard mass flux. And here, the mass density is measured in the comoving frame of the fluid. And that's why we have a Lorentz factor appearing. So this is mass conservation. Then energy conservation. So to get the energy conservation, I have to multiply the mass density or the mass flux times the energy per unit mass, and I get the energy flux, which is constant if it is an adiabatic outflow. So what is H? H here is the specific enthalpy, so the enthalpy per unit mass. So this is something which is C squared for the rest mass energy, plus epsilon, which is the internal energy per unit mass, plus P over rho. This is to get an enthalpy. And for a perfect fluid with an adiabatic index gamma, it is even like that. And then, as I assume an adiabatic expansion, I can use my adiabatic invariant. Okay, so these are my 3 equations. You see that I can easily divide the second equation by the first one, and I get a new equation, which is just enthalpy times Lorentz factor equals a constant. Okay. So you see that in the enthalpy, there are 2 terms, the rest mass energy and the internal energy. So initially, when energy is released very close to the central engine, it is released in this purely hydrodynamical model as thermal energy, and the thermal energy is dominant compared to the rest mass energy. So it will be the first phase of evolution of my fireball. The phase where the internal energy is dominant. So in this case, as we need a very high density of energy, we are usually dominated by the density of radiation, and then we can assume an ultra-relativistic adiabatic index for some. So what is my new set of equations? Conservation of mass. Conservation of energy, I can replace H by, I can split gamma, and okay, gamma over gamma minus 1, P over rho gamma. And I still have P over gamma proportional to rho. So from the first equation, I can get the dependence for the density. The density is proportional to 1 over the square of the radius times the Lorentz factor. Then from the third equation, I can get the dependence for the pressure. So it's the same as rho, but to the power gamma. And gamma is 4/3, so it's 1 over 8/3, and gamma 4/3. And then I can replace here. I get something which is gamma proportional to rho over P, which is 1 over R squared gamma and R8 squared gamma for third. Sorry, so if I write it here, I get gamma proportional to gamma proportional to 8 thirds minus 2, it's 2 thirds, and gamma 4 thirds. And so finally, gamma is proportional to R. If I know that gamma is proportional to R, it means that I have an acceleration. I start from a very low Lorentz factor, and then in this simple fireball model, the Lorentz factor is just increasing linearly with the radius. And you see that in this case, the density is decreasing due to the spherical expansion, is decreasing like 1 over R cubed. So this is my first phase, my phase of acceleration. And then, of course, because of the decrease of density and of pressure, it's easy to show from this relation that this quantity is decreasing, and at some point it will become smaller than c squared. So it is the second phase in the evolution of my fireball. Now a phase where the rest mass energy is dominant compared to the internal energy of my fireball. So in this second phase, I can still write conservation of mass. And the conservation of energy, which is h gamma equals constant, becomes c squared gamma equals a constant. So it's a very simple phase. Gamma is a constant. So it means that acceleration is finished. I have converted all my internal energy into kinetic energy, and now I'm just evolving with a spherical expansion with a constant Lorentz factor. And then in this case, it's easy to see from this equation that the density is now decreasing only like 1 over R squared. So it's a very simple theory. It gives a practical estimate for the saturation radius. From this equation, you see that the final Lorentz factor is just the ratio of the injected energy divided by the injected mass. And then from the linear relation between Lorentz factor and radius in the acceleration phase, it's easy to find that this Lorentz factor is reached at an acceleration radius, which is just given by the initial size of the central source times the final Lorentz factor divided by the initial Lorentz factor that you can take equal to unity. So it's just the product of the initial size times the final Lorentz factor. So in a fireball model, if you want to reach a Lorentz factor of 100 with a source of size r dot, it's easy. You reach it when you reach a radius, which is 100 times r dot. Okay, so this is a fireball. It's important to know these scaling laws, because even if they are not very realistic, in particular in most realistic models, the magnetic field plays a role and affects these scaling laws. Even if it's not realistic, it's a reference which is used in many publications for comparison. And just a last point to mention before coming back to the slide, this is about my initial approximation, the fact that I have considered each layer in the fireball evolving independently of the other layer, which was a simplification to use a steady state approximation. In fact, this approximation is valid as long as the relative velocity between different layers in the fireball, which is in unit of C delta beta, times the time since the ejection, which is R over C because we are moving at relativistic speed, is small compared to the initial size of the fireball, the width of the fireball. It means that the propagation due to this relativity, the width corresponding to the propagation with this relative velocity is a correction which is small compared to the true width of my fireball. And it's easy to see that this is of the order of 1 over 2 times the square of the minimum Lorentz factor in the fireball, because you know that in the ultra-relativistic limit, beta is given by 1 minus 1 over 2 gamma squared. So it gives a limit which is called the spreading radius. Below the spreading radius, interaction between layers are negligible, and the spreading radius is of the order of 2 gamma mean square and the initial size of the fireball. Okay, so I have now two important characteristic radius, acceleration radius, spreading radius. I can come back to my slides. Okay. So I show here a full calculation of the fireball model. So here you have the Lorentz factor as a function of the radius in unit of the initial size of the source. So you see clearly the linear acceleration in the first phase and then the saturation in the second phase. And the acceleration radius that I have estimated is given by this dashed line, so it's a good estimate. And here I have shown for the same case the evolution of the two energy reservoirs. In dotted line, you have the thermal energy, and in solid line, you have the kinetic energy. And you see clearly the conversion from thermal to kinetic energy. So the fireball is very efficient because you see that at the end, 100% of the thermal energy is converted into kinetic energy. It is valid as long as the evolution is adiabatic. Of course, if you have strong radiative losses before the acceleration radius, then it could be invalid. But we will see that at the acceleration radius, the ejecta is still opaque, so adiabatic expansion is an excellent approximation. The problem is not here, is the fact that there is no realistic way to produce such a fireball, and in more realistic situation, you have a magnetic field, so part of the energy is magnetic, and the question of conversion of magnetic energy into kinetic energy is much more complex. Okay, so before I switch to the next topic, I don't know if you have questions about the two calculations I just did. So the fact that we need a high Lorentz factor and the fact that the scaling laws obtained with the fireball model. Is it clear? I hope so. So if there are no questions, then I will go on. And so now we have produced a relativistic outflow, and we want to produce the prompt emission. So here there is a old argument, which I think is due to CPRAN, which is the fact that sorry, I have a question, which is to explain again this curve, the energy curve. So I explain it again. The x-axis is the same as before. This is the radius. And there are two curves. One is a dotted line. This is the internal energy reservoir. And in black, this is the kinetic energy reservoir. So initially, in the firewall model, all the energy is deposited as thermal energy. And during the first phase of the spherical expansion, the Lorentz factor is increasing linearly with radius, which means that physically we convert thermal energy into kinetic energy. And this is exactly what we see. You see the kinetic energy rising here and the thermal energy decreasing here. And when you reach the acceleration radius, which sometimes it's also called the saturation radius, it is the moment where the conversion is more or less finished, and then kinetic energy is constant, and thermal energy is just very low. You have converted 100% of your thermal energy into kinetic energy. That's why I say that this model is very efficient. Unfortunately, it's not realistic. Okay? So now that I have a relativistic outflow, I would like to produce prompt gamma ray radiation. And the old argument from Piran is the following. When you observe the variability in the light curve of the gamma ray burst, you see that the variability is not evolving during the burst. You can have short timescale variability at the beginning, in the middle, or at the end of the light curve. And this is a strong argument to say that it is associated to a dissipation mechanism which is internal to the, which is within the outflow. Because if it was associated to the deceleration of the outflow by the external medium, in this case, we would say that it has an external origin, then typically the main source of emission is a strong forward shock which is propagating within the external medium. And for this forward shock, as the radius is increasing and the Lorentz factor is decreasing, the typical variability timescale that you can reach is just increasing with time. So in external shock model were considered for the prompt emission at very early time, but they were predicting a variability timescale which was increasing with time in the light curve. And then it can be ruled out for this reason, and we have to find an internal mechanism. So there are a lot of possibilities discussed today. The idea is that there is a first important radius that we will derive in 1 minute, which is a so-called photospheric radius. The photospheric radius corresponds to the transition for the ejecta from an optically thick regime to an optically thin regime, or you can say from an opaque to a transparent regime. Before the photospheric radius, radiation cannot escape. And above the photospheric radius, radiation can escape. So clearly, there is a first possible emission site, which is the photosphere. So it is considered, I will discuss that in a few minutes. And then you can also imagine that there is internal dissipation in the jet above the photosphere. And in this case, we have typically models where the emission is due to optically thin synchrotron emission from non-thermal electrons accelerated either in shocks or in reconnection events. And note that all these possibilities can sometimes coexist. For instance, it's very possible to have a component emitted at the photosphere when the ejecta becomes transparent, and to have a component emitted above the photosphere with accelerated electrons, either in shocks or in reconnection. What is probably not possible, even if, for instance, Bing Zhang has imagined a possibility to avoid the problem we mentioned, this is the combination of shocks and reconnection, because in principle, to have an efficient reconnection model, you need a high magnetization in the region where the dissipation occurs. And if the magnetization is high, in principle, shocks cannot propagate. Okay? So I will derive the two radius which are given here, which are two characteristic radius which are important. The first one is the radius where the photosphere is reached, the radius where the ejecta becomes transparent, And the second radius is a typical radius for internal shocks. And you can consider that more or less it's also a good estimate for the radius of reconnection. So the idea is that this radius is very simple to estimate. This is exactly the same calculation as what I just did for the spreading radius. The idea is that if you want to have collision between different layers in the ejecta, you need these layers to have different velocities, and the radius where the collision will take place is related to the initial difference of velocity, so the initial relative velocity. So it's exactly the same calculation as before, and so the estimate of the internal shock radius is given by the spreading radius. So if I put number, for instance, if I take a Lorentz factor of 100 and a typical size for my ejecta of the order of 1 second, typically this is what would lead to the production of a pulse in the light curve with a duration of 1 second. Then I have a typical radius which is 10 to 14 centimeter, 10 to 15 centimeter. It's very high compared to the initial size of the central region. And I will take the question just afterwards. And I will now compute the photospheric radius. And you see that the photospheric radius is typically 100 times smaller than the internal shock radius. So on the plot here, the order of characteristic radius is correct. You first reach the photosphere, and then you have internal dissipation with shocks or reconnection above the photosphere. And later, I will compute the radius where deceleration starts, and we will see that this radius is even larger. Okay, so before doing the calculation of the photospheric radius, I see that there is a question. Yes, a question about the reverse shock. It's a good question. If you agree, I will mention that later when I will discuss the deceleration, because the reverse shock is, of course, associated to the deceleration. But the idea is that when the deceleration will start, we will have a reverse shock propagating in the ejecta. And then, of course, if the deceleration starts very early, it can affect the internal dissipation mechanism, either the internal shocks or reconnection. If you prefer reconnection models, it means you assume high magnetization, and then probably the reverse shock won't propagate. If you prefer internal shocks, it means you assume a low magnetization, and then the reverse shock can propagate and interact with internal shocks. The point is that I will show that for standard parameters, the radius where deceleration starts is much higher than the internal shock radius. So in principle, you should avoid this interaction between the reverse shock and internal shocks. But there is a space in the parameter space, there is a region in the parameter space where you can have such an interaction. Okay, so I will come back to my blackboard to compute the photospheric radius, which is a very important characteristic radius, because all the emission we receive has to be produced at this radius or above. Before this radius, we have no direct electromagnetic signal. In the future, we hope to receive gravitational waves. We have one case for a short gamma ray burst, or to receive neutrinos, but for electromagnetic radiation, no hope. Okay, so I come back to okay. And so now the photosphere. So the idea is quite simple. Assume now that you have a relativistic layer with a certain width delta, and it's moving with the Lorentz factor gamma. And assume that you emit photons and you want them to escape the layer in the direction of the observer. The observer is somewhere here. So the idea is, again, to compute the optical depth for these photons and to check when this optical depth becomes smaller than unity. This is when you become transparent. Here, we have to discuss what is the dominant process for the interaction between photons and matter. And we are in conditions which are very different from the central engine because we are far from the central engine. And we could show that the dominant process is just Thomson scatterings on free electrons. So I will just consider the Thomson cross-section for the interaction. So in this case, I can compute the optical depth. It will be an integral from the radius where the photons is emitted to the radius where the photon escape from the relativistic layer. This radius is easy to compute. You just have to take into account the width you need to cross and the relative speed between photons and the layer. And the difference of speed due to the ultra-relativistic motion is just c divided by 2 gamma squared. So in this case, it's easy to show that the escape radius is the emission radius plus 2 gamma squared times the width of the relativistic shell. And then I will compute this optical depth in the comoving frame of the relativistic layer. So I have the length crossed by the photon times the density of matter times the Thomson optical, the Thomson opacity. For those who are not familiar with the concept of opacity, in astrophysics, an opacity is a cross-section per unit mass, whereas a cross-section is a cross-section per particle. Okay. So let's compute the length dl prime. dl prime can be related to dr in the fixed frame by a Lorentz transformation. Here I am in the comoving frame of the relativistic layer, so I have to take into account for the Lorentz transformation, the Lorentz factor and the beta of this layer. And I'm considering a length crossed by photons. So in the fixed frame, photons move at the speed of light. So dr is cdt. So in this case, dl prime is just given by gamma 1 minus beta c dt. And if I take, as usual, the ultra-relativistic limit, 1 minus beta is 1 over 2 gamma squared. This is dr divided by 2 gamma. I mentioned that this is important to well understand this part, because if you do not perform correctly the Lorentz transformation of the length here, you can have a completely wrong scaling for the photospheric radius as a function of the Lorentz factor. So it's important to be careful here. Okay. Then it's more easy to estimate the rest mass density in the comoving frame. If the shell has a mass m, this mass is included in a volume which is given by 4 pi r squared times delta, the width of the shell, but this would be the mass density in the lab frame, and I have to divide by gamma to go in the comoving frame. Okay, so you see that now I have everything to compute my optical depth. So m over 4 pi delta gamma. I have 8 coming from these two and a gamma square coming from this gamma. I have the Thomson opacity here, and then I just have the integral of dr, and you see that I have 1 over r square here, so it's dr over r square from r to rs. So what is this integral? It is 1 over the escape radius minus 1 over the emission radius. And from the expression which is here, it is given by that. Ah, sorry. Oops. Okay, so you see I have all ingredients, and then I can easily compute for which radius r, tau becomes of the order of unity. For smaller radius, tau is larger than unity and my layer is opaque to photon. And for larger radius, tau is smaller than unity and my layer is transparent. So the transition is for unity, and this is the corresponding photospheric radius. So you see that in principle it's a complex equation because of this factor, but we can show that this radius, the photospheric radius I will get, is below the spreading radius, which is given by that, meaning that I can neglect r in front of 2 gamma squared delta, and then this equation is just 1 over r. So in this case, it's very easy to estimate the photospheric radius. Photospheric radius is given by the mass of the layer times the Thomson opacity divided by 8 pi, the width of my layer, and the Lorentz factor squared. And usually you use an alternative expression for this formula. You can say that m is a mass flux times a certain duration. For instance, the duration of the relativistic ejection by the central engine, and that the width is the same duration multiplied by the speed of light, because everything is moving at the speed of light. So we get this new expression. And then from what I said before, m dot is just E dot divided by gamma c squared. And I get this final expression. So it's important, I get the final dependency on the Lorentz factor. It's varying strongly with the Lorentz factor. It's like 1 over gamma cubed. If the Lorentz factor is very high, the photosphere is very close to the central engine. If the Lorentz factor is very low, then the photosphere can be at much larger radius. Okay, I don't know if there are some questions about this derivation. Otherwise, I will come back to my slides. So this radius is really a very important one in gamma ray burst theory, because, as I said, all the emission we receive must be produced either at this radius or above. I should mention that here I made the calculation in the simplest case, where I consider photons propagating radially in the direction of the observer. If you start to consider photons escaping with a direction which makes an angle compared to the radial direction, the calculation is more complicated, and the photospheric radius depends strongly on the viewing angle. So, for instance, for modern models of the outflow where there is an angular structure, like what I will discuss tomorrow, for instance, for 170817, the calculation of the photospheric radius becomes really tricky and usually has to be performed numerically. It's difficult to do it entirely analytically, like what I did here. Okay, so no question. I come back to my slides. Okay, so now I know where the ejecta becomes transparent, and I have also estimated where dissipation mechanism like shocks or reconnection could occur. I will discuss later how this dissipation leads to gamma ray emission. Here I'm focusing on the characteristic radius in the model. And so finally, there is a last stage in the evolution of my ejecta. First, it becomes transparent. Second, it dissipates some energy with internal mechanism. And finally, it will be decelerated by the external medium. And because of the much longer time scales observed in the afterglow, it's very natural to associate the afterglow with this deceleration. Another argument is the fact that the deceleration will lead to an ejecta which is initially highly relativistic, highly energetic, and then Lorentz factor is decreasing, energy is decreasing, and so naturally it will lead to an afterglow emission which is initially very bright, peaking at high energy, for instance in X-rays, and then with time becoming fainter and fainter with a typical photon energy which enter longer wavelengths. So I will compute now the last characteristic radius I need for modeling gamma ray burst, which is the so-called deceleration radius, the radius where this deceleration starts. And I will say later that in addition to the forward shock propagating in the external medium, which is really a strong ultra-relativistic shock and which is probably responsible for most of the afterglow emission, as I said before, in addition to this shock, there is also a reverse shock which is propagating in the ejecta. So in terms of region, on an hydrodynamical point of view, the situation is quite complex. From right to the left, you have first the unshocked external medium, then you have the shocked external medium, you have a so-called contact discontinuity, which is the separation between the ejecta and the external medium, and then you have the shocked ejecta, shocked meaning here shocked by the reverse shock, and the unshocked ejecta, which can have a complex structure if reconnection or more naturally internal shocks are propagating within it. Okay, so you have clearly 4 regions. It's difficult to derive the full hydro of this complex hydrodynamical problem, so I will focus on the dynamics of the forward shock, which is simpler because there is a self-similar solution which has been derived by Blanford and McKee, and which is the relativistic analog of the well-known Sedov solution for supernova remnant. Okay, so this derivation can be done now. So I will derive it in a very simple way because it's an approximate way, because the full derivation of the self-similar solution is quite technical. So here I will just use an energy conservation argument based on the idea that radiative losses from the afterglow are negligible. Of course, if it is not the case, the dynamics can be affected. So what is my initial energy reservoir? This is the kinetic energy of my ejecta. So now the zero index means initial condition of the ejecta before the deceleration. So it's not the real initial condition because maybe the ejecta has already been modified by internal shocks, for instance. So this is my initial energy in my ejecta. And I have also some rest mass energy in the external medium. Mx is the mass of swept up material from the external medium by the ejector. And if I have energy conservation, once the ejecta starts to be decelerated by the ambient medium, its kinetic energy becomes gamma m0 c squared, where the new Lorentz factor is lower than the initial Lorentz factor. This is a deceleration. And the energy has now been transferred in the shocked external medium. So the mass of this shocked external medium is mx. In the condition of strong ultra-relativistic shock, it can be shown that the internal energy in the shocked region per unit mass is just gamma c square in the comoving frame. And to come back in the lab frame, I multiply by gamma, so I have a gamma square. So you see that depending on which term is dominant on the left and on the right side, you can have different regime for the evolution of the Lorentz factor of gamma as a function of the swept up mass mx. So first phase, the kinetic energy of the ejecta is much larger than the rest mass energy of the external medium. And the energy of the shocked external medium is still negligible compared to the kinetic energy of the ejecta. In this case, the two dominant terms are this one, and it's easy to show that this is the case before the deceleration. The Lorentz factor is equal to the initial value. In the second phase, these terms becomes larger than this one. So the first condition is the same, but the second condition is the opposite. So now my equations reduce to that. And you see that the consequence is a decreasing Lorentz factor. And as this is a constant, the Lorentz factor decreases like the swept up mass to the power minus 1/2. So for instance, for a uniform medium, if the medium is uniform, the swept up mass increases like the volume, like R cubed, and the Lorentz factor goes like R to the power minus 3/2. If you have a stellar wind, which is possible for long GRBs which have massive star progenitors, then in a stellar wind, usually the density goes like 1/r squared, and then the mass just increases linearly with the radius. So you have this scale. Okay. So when is the transition between these two phases? This is when these two terms are equal, and then it's easy to show that the transition is for a swept up mass which is equal to the mass of the ejecta divided by its Lorentz factor. It's funny, for non-relativistic motion, if you want to decelerate a mass m, quite logically, you have to put another mass m in front of it. Okay, if you want to stop an elephant, you do not need to put a hunt in front of the elephant, you need to put a second elephant. And in relativity, special relativity, the result is not very intuitive. If you want to stop a mass m with a Lorentz factor gamma, you just need to put in front of it a mass m over gamma. So this is our result. And from this estimate, I can deduce the corresponding radius, which is the deceleration radius. Okay. And then I can mention a last phase in the evolution. As the swept up mass is increasing with time, at some point, this term, the rest mass energy of the external medium, can become larger than the initial energy of the ejecta. And this is, of course, the moment where the ejecta will become non-relativistic. So in the last case, if the rest mass energy of the external medium becomes larger than the initial energy of the ejecta, then the equation becomes that, meaning that the Lorentz factor is 1. This is a Newtonian regime. The ejecta is not relativistic anymore. And in this case, we recover the Sedoff solution. Okay? So, I don't know if you have questions about the derivation I just did. Okay, it seems not. So I come back to my slides. Oops, sorry, I made a mistake. Okay. So I show here the full solution for the deceleration when you solve the equation I have written a few minutes ago. So first phase, no deceleration, then power law decay in the deceleration phase. The transition here is the first dashed line is the deceleration radius. And then second transition, the Lorentz factor becomes of the order of unity. The motion becomes Newtonian, it's a Sedoff solution. And the second characteristic radius here is the Newtonian radius. So as you have seen, this transition corresponds to a swept up mass, which is m over gamma. And this is how I can deduce my deceleration radius, which is given here. You see that the internal shock radius I have derived was typically 100 times larger than the photospheric radius. And you see that the deceleration radius I derived is again 100 times larger than the internal shock radius. So it means that in the most standard case, you should not have too much overlap between the three phases: transparency, internal dissipation, deceleration. But of course, there are strong dependency on the Lorentz factor, on the energy, on several parameters for each characteristic radius. And so you can explore some region in the parameter space where you have some interaction. For instance, when you start to have internal shocks before the photosphere, or when you start to decelerate before the end of internal shocks, things like that. Here I show the same curves, Lorentz factor as a function of radius, but I have also plotted velocity as a function of radius to show that once the Lorentz factor is of the order of unity, so when you enter the Newtonian regime, you recover the usual Sedoff scaling law, which is well known in supernova remnant physics. And the difference between the left and the right in this plot is the nature of the external medium. Here I have plotted the solution for a uniform medium, and here for a stellar wind. And in blue, I have given some estimate of the observer time for photons emitted by the forward shock at this radius. So to estimate this observer time, I have to take into account that the photons is emitted at a certain radius r and at a time t, and to reach this radius, it has propagated at the speed of the ejecta, so beta, and then it's propagating at the speed of light to reach the observer, and the distance to cross is the full distance to the observer minus r, which has already been crossed. And at the end, you get this expression for the observer time, where the 1 over 2 gamma squared comes again from the relative speed between photons and matter. Okay, and usually the d over c term is just neglected in all these equations because it's just a question of definition of the origin of time for the observer. Okay, so this is just a constant. So the important term is this one. And so using this equation, I give an estimate of the observer time during the deceleration, and you see that you can easily have an afterglow evolution over several days, like what is observed, and that to observe the non-relativistic phase, you have to follow your ejecta for typically several months or even 1 year or more. It's typically, for instance, something which is possible for nearby burst. For instance, a famous bright nearby burst, which is 0329, I think has been followed with radio observation for several years. And so it's a very good case to check this transition. You see that when the external medium is a stellar wind, as the density the external density decreases with radius. The deceleration is less steep. The slope is not the same here, but the transition to the non-relativistic phase occurs more or less at the same radius. So the deceleration radius is earlier, but the deceleration is less steep, and the Newtonian transition is at the same radius. Okay. So here, I have finished to describe the whole scenario. I have explained where the different phase of emission can take place. And now in the remaining time, but I think that the remaining time will be tomorrow, I will give more details on some aspect of this scenario. I will try to give some details about the physics of the progenitor. How can we go beyond the simple fireball model? I will try to give some details about the prompt emission. For instance, I will discuss a little more the difference expected between emission at the photosphere or in internal shocks and reconnection, and what are the expected radiative processes which shape the spectrum. And I will also give more details about the afterglow. And what I would like also to do, so I will have to think a lot about the organization of my last lecture because I was a little slower than I expected, I would like also to discuss the special case of the 170817, which is a very interesting case because everything that I have described for the first time is detected by an off-axis observer, whereas usually for gamma ray burst at cosmological distance, because of the strong relativistic beaming, we can detect it only if we observe it on axis. And so it's a major difference, and it helps a lot to learn things, for instance, about the real geometry of the ejecta. So I will discuss that. So if there are, I think that for the lecture, I will stop here, but of course, if there are additional questions, I can take them now.
Thank you, Professor Daigne. I think there are a few questions in the chat box.
Okay.
I think the first question is by Ankur on Newtonian phase, and maybe we'll start with that one.
Okay. So in the Newtonian phase, more or less, you recover the same kind of physics than for the supernova remnant. And in fact, it leads to an interesting question. How is it possible to distinguish a very old GRB remnant and a very old supernova remnant? The difference, of course, is in the initial energy release. So you can expect some differences, but more or less in the same physics at very old times. So in the Newtonian phase, you still have a forward shock. Now it's Newtonian. Electrons are accelerated at the shock and radiate by synchrotron radiation, like in the Crab Nebula or an object like that. Okay.
Second question.
One complement. I will discuss briefly tomorrow the fact that if the geometry of the ejecta is indeed a jet, when the jet is ultra-relativistic, the lateral expansion is negligible because due to the Lorentz transformation, if you have some motion at the sound speed in the comoving frame, when you come back to the fixed lab frame, in the transverse direction, the speed is divided by gamma, so it's very small. But when you enter the Newtonian regime, now lateral expansion can become very important. And so at very old times, you expect to lose the jet geometry and to become more or less spherical at very late times. Okay. Then I see that there is a question about the diversity of afterglow emission. So as for one single event, you have seen that as it's a long process, the deceleration of such an energetic outflow, there is a broad range of timescales. You can expect emission from, let's say, 1 minute to several years if you are sensitive enough. And then tomorrow I will show that this emission is evolving. Not only the flux is decreasing because of the deceleration, but the spectrum is evolving. So for instance, for late observation, it's only in radio that you have a good hope to observe it. But then we observed a great diversity of behavior from an afterglow to another one when you have a catalog of afterglows. And here, your question is an excellent one, and it's very difficult. What is the origin of this diversity? It can be partially due to a diversity of external medium. For instance, if the density is not always the same, the deceleration won't start at the same radius. But some of the diversity is associated to some variability in the observed afterglow light curves, for instance, X-ray flares or plateau phases. And this is difficult to explain just with some variations around the external medium. Probably it is related either to some details of the internal structure of the ejecta, or to some evolution of the central engine itself, for instance, with some late activity. I will try to mention that briefly tomorrow. So your question is an excellent one, and I would say that there is no consensus yet for the answer. Okay.
Is any?
I think I missed one question during the talk about the question, the ejecta is baryon dominated or Poynting flux dominated. I will say a word about that tomorrow. In fact, we don't know exactly. And the answer is maybe not the same at early times and at late times. Probably very close to the central engine when the jet is launched. If I have to make a guess, it is Poynting flux dominated. But then the question to know how it evolves with propagation and what is the final magnetization is complex. If the efficiency of the conversion of the magnetic energy into kinetic energy is low, it's still Poynting flux dominated at large radius, and then the best candidate to produce the prompt emission is reconnection. And after reconnection, you can come back to a baryon dominated regime because you have destroyed your magnetic field. Or if you have an efficient conversion of magnetic energy into kinetic energy, then you can recover a baryon dominated regime much earlier, and for instance, allow for internal shocks and a reverse shock. It's a complex question because it's related to the physics of the acceleration of the jet, which is a very complex one. And
right, and I think, okay, we'll take this as the last question by Resmi, who has channeled the previous question by Mukesh.
Yes, sorry, I forgot also this question. Yes, I mentioned briefly synchrotron radiation today. I will give more details tomorrow. So in internal shock, also in reconnection, also in the external shock for the afterglow, the dominant process is probably synchrotron radiation. So indeed, we need not only to accelerate electrons, which can be done in shocks, for instance, but we need a magnetic field. And again, we have a complex question. If the magnetization is low, far from the source, what is the origin of this magnetic field? The answer is probably provided by the same answer than how do you accelerate particles. If you want to accelerate electrons at a shock, you need electrons to cross several times the shock. This is a so-called Fermi acceleration process. And for that, you need the shock region to be magnetized to allow electron to diffuse, to scatter and to come back towards the shock. And so the idea is that there are plasma instability in the shock region which amplify a local magnetic field even if it's very low initially. So you could have a turbulent amplified magnetic field in the emission region associated to the same plasma physics than the acceleration of particles.
Very good. So please remember that Professor Daigne will have another lecture tomorrow at 1:30. Today we will break in a few seconds and then we will reconvene because the program is still ongoing. So the next talk will be at 3:30. But for now, let's thank Professor Frédéric Daigne once again for a wonderful lecture. Thank you very much. There are ways of expressing your reactions in Zoom, and perhaps people are already familiar. But with that, thanks again, and we break for a few minutes.
Okay, thank you very much. And I will provide my slide with also the scan of my blackboard calculation. Okay.
That will be very helpful.
See you tomorrow.
Thank you, Dr. Frédéric. Bye.
Thank you.